बिस्मिल्लाहिर्रहमानिर्रहीम। वेलकम बैक टू मैथमेटिकल मेथड्स ऑफ फिज़िक्स। आज हम लेक्चर नंबर 10 स्टडी करेंगे इस कोर्स का। लास्ट लेक्चर में, लेक्चर नंबर 9 में हमने ग्रीन्स फंक्शन शुरू किए थे, जिसमें हमने डायरेक्ट डेल्टा फंक्शन की प्रॉपर्टीज़ देखी और उसके बाद ग्रीन्स फंक्शन डेवलप किया इन वन डायमेंशन। आज हम ग्रीन्स फंक्शन से ही स्टार्ट लेंगे, उसी टॉपिक को जारी रखेंगे और फर्दर ग्रीन्स फंक्शन की प्रॉपर्टीज के बारे में स्टडी करेंगे। सो टुडेज आउटलाइन इज प्रॉपर्टीज ऑफ ग्रीन्स फंक्शन एंड देन वी विल गो ऑन टू सी एग्जांपल्स ऑफ ग्रीन्स फंक्शन। सो लेट्स स्टार्ट विद द प्रॉपर्टीज ऑफ ग्रीन्स फंक्शन। दिस इज द इक्वेशन which is a solution of this differential equation, and this is exactly same thing which we studied in the last lecture. If you look at the last slide of last lecture, it's exactly the same. So in last lecture we proved that this integral type of equation was the solution of this equation, which was which gives you the deflection of string with distributed load. Alright, so if this is a solution of this equation, this y must satisfy this equation. So if I replace this y by this integral and bring this derivative inside, I'll get this. And from here we stated that this expression d square tg by dx square, this should be equal to the delta function, so that the integral with the w eta gives you wx. Right? This was the property of delta function, this property which is stated at the end of this slide. W eta delta x minus eta d eta will give you wx. Alright, so here this thing should be equal to delta x minus eta with the minus sign. So if we integrate this colored equation, which is this one, if we integrate this red equation, because we are having second derivative of Green's function, so let's integrate it. If we integrate from a to a plus 0 at this point a, we obtain t was constant, brought it out, second derivative of g x eta d eta. So we are integrating from a minus 0 to a plus 0, which is given by this one, because right hand side is delta x minus eta of the equation. And since we know that this integral, the area under the curve is 1, because you see there is no contribution on the left and on the right hand side, because on the left of a is 0, on the right of a it's 0. Alright, so even if we integrate from a minus 0 to a plus 0, it will still give me 1, right? Because from minus infinity to a and from a to infinity there is no contribution. Contribution is only at a. So it's, if I'm just left of a and just to the right of a, this gives me the whole area. So integral of the second derivative gives me the first derivative. So first derivative of g with respect to x from a minus to a plus, from a minus to a plus, is equal to -1. Hence the jump at x is equal to eta for this problem is this one. You see, if I divide the, t on the right hand side, I got this one. So it means the derivative of g with respect to x has a jump at a, right? So see, a plus 0 and a minus 0 gives you -1 by, which is a downward jump. Thus when the tension t is equal to 1, this jump is -1 at x is equal to a. Negative shows that this is a downward jump. Alright, so if tension is 1, then it's exactly equal to -1. So a function fx has a jump lambda at x is equal to eta if and only if the respective right and left hand limits f eta plus 0 and f eta minus 0 exists as x tends to eta, and f eta plus 0 minus f eta minus 0 equal to lambda. So if the difference between the right and left hand limit is equal to lambda, we call lambda the jump of the function. So what happens is, if you look at just to the left of eta, it is, and if you look at just to the right of eta, so there is a difference of lambda. It means your function has a jump at eta. Alright, so on the left it was here, on the right it was here. So there is a difference between the right and left hand limits. This is right hand limit, this is left hand. So there is a jump of lambda. If the difference is lambda, we call this a jump lambda. Like a step function, I just defined in the last lecture the Heaviside function. What was the Heaviside function? In Heaviside function, we had a jump of 1 unit, because on the left it was 0, on the right it was 1. So there was a jump of 1. So Heaviside function has a jump of 1 over there. All right. So the jump lambda is said to be upward or downward depending on whether lambda is positive or negative. So if this lambda is positive, the jump is upward. If lambda is negative, the jump is downward. All right. If the function is continuous at eta, then the jump is 0. It means there is no jump. For a continuous function, there is no jump. Whenever a function jumps up or jumps down, there is a discontinuity over there. So if a function is continuous somewhere, it will not have a jump over there. Sometimes this jump is called jump discontinuity. So itself it is a discontinuity. If the Green's function is this one, this is the same Green's function which we obtained in the last lecture, gx eta L minus eta x over TL and 1 minus x eta by TL. Then partial g by partial x has a downward jump of negative 1 over t at x equal to eta. We proved it over here as well. We can prove it from here as well. So this is basically, this gives you the proof of this statement, one more proof of this statement. So if we take the limit as x goes to eta plus 0, right? If you take the limit eta plus 0 means x is greater than eta, this one. We are here. So what is the derivative? Derivative is minus eta by TL. Minus eta by TL. So there is minus eta by TL, that's it. There is no x in here. So if you take eta minus 0, it means you are in this interval. X is less than eta. Less than eta means you are in this interval. So if you take the derivative with respect to x, you will get L minus eta by TL. L minus eta by TL. So now if you take the limit, you will get L minus eta by TL. Alright. So therefore, partial g by partial x at eta plus 0 minus partial g by partial x at eta minus 0 is equal to minus 1 over t. Alright, so if you take the difference between these two, of course eta by TL, they cancel out, and 1 over t, TL over TL will be left, so it is just 1 over t. Alright, this is L basically, this is L minus eta, L minus eta. Alright, so L and L cancelled out, you are left with just 1 over t. This is a downward jump. You can easily see that this is lambda is 1 over t here and with a negative sign. So lambda is negative 1 over t, it's a downward jump of 1 over t. So we proved it here as well. We proved from this equation, we proved this from this red equation that the Green's function has a jump, the derivative of Green's function has a jump of negative 1 over t. We proved it the same thing from here. Alright. So this is one of the properties of Green's function, that its derivative has a jump of negative 1 over t. Green's function consists of two linear expressions. It satisfies the linear homogeneous differential equation t y double prime is equal to 0 at all points of the interval 0 less than eta except at x equal to eta. The reason is, as your Green's function satisfies this equation, see t comes out, so t g double prime is equal to delta x minus eta. So whenever x is not equal to eta, the right hand side is 0. What is delta function? Delta function is always 0 when x and eta are not equal. So when x is not equal to eta, it's 0 on the right hand side, and you get this equation. Ty double prime is equal to 0 when x is not equal to eta. That's what we said, except at x is equal to eta. If x is equal to eta, the right hand side becomes infinity. Alright? Since the second derivative does not exist because dg by dx is discontinuous at that point. You see, here you see, we have a jump at eta. At eta, dg by dx at eta has a jump discontinuity. So second derivative will not exist at that point. A point where function is discontinuous, the derivative does not exist there. So partial g by partial x has discontinuity at eta, so the second derivative will not exist at eta. So that's the reason this is true only if x is not equal to eta. Alright? So let's consider another example. Let's consider another definition. Consider the second order homogeneous differential equation y double prime plus pxy prime plus qxy is equal to 0. This is a general second order homogeneous. The right hand side is not is equal to 0, so that's why it's a homogeneous differential equation. And with homogeneous boundary conditions as well, that at x is equal to a, your alpha 1 y at a plus alpha 2 y prime of a is equal to 0, and at b your beta 1 yb plus beta 2 y prime of b is equal to 0. So these both boundary conditions are also homogeneous, where alpha 1 and alpha 2 both are not 0 and beta 1 and beta 2 both are not 0. So they both cannot be equal to 0. One of them can be equal to 0. Let's say if the condition is y at a is equal to 0, it means alpha 2 is 0. And if y prime of a is equal to 0, it means alpha 1 is 0. But both simultaneously cannot be equal to 0. Similarly here, beta 1 and beta 2 cannot be 0 simultaneously. The reason is, if they both become 0 simultaneously, then this whole thing disappears. So we must have two conditions for second order ODE. So we must have alpha 1 of alpha 1 and alpha 2 not equal to 0, and 1 of beta 1 beta 2 not equal to 0. So consider a function gx eta which satisfy the above differential equation. If this satisfy the above differential equation, what we do is we replace the left hand side, we replaced y by g, but the right hand side is replaced by delta function with a minus sign, right? This is what we got. See, our differential equation was t d2y by dx square. So we got t d2g by dx square. Left hand side y is replaced by g, but the right hand side is replaced by delta function. So we have to do the same thing here as well. That the left hand side y is replaced by g. G is our unknown function now, but the right hand side will be replaced by the delta function. With the following properties, the property is that your Green's function satisfy homogeneous boundary conditions at a and b, and your at x is equal to eta, your g should be continuous, alright, but your derivative of g should have a jump discontinuity. Alright, your derivative should have jump discontinuity. So these are two extra conditions on the Green's function. It will satisfy the conditions given by the problem, which is the homogeneous boundary conditions. These will be satisfied, but Green's function also has the property that g itself should be continuous in a to b, and it should have the derivative of g should have a jump at x is equal to eta, where eta lies between a and b. So then this function is called the Green's function of the problem defined by the given differential equation and its boundary condition. So any function that satisfies this differential equation along with all these properties will be called a Green's function of this boundary value problem. So corresponding to every boundary value problem, we can define a Green's function. Alright? So let's see examples how we can construct Green's functions for different boundary value problems. Alright? Of course, this will be a very intensive exercise of examples here, and you need to watch it very, very carefully, and if possible, just do them on your own as well. Alright? So first example is, construct a Green's function for the equation y double prime plus y equal to 0 with the boundary conditions y0 and y pi by 2 is equal to 0. Here you see alpha 2 is 0 and beta 2 is 0. Both are not 0 at once. Alright, so let's start with this example. So first example, y double prime plus y is equal to 0 with boundary conditions y at 0 is equal to 0 and y at 0 is equal to 0 and y at pi by 2 equal to 0. So this is our equation. Alright, so we need to construct the Green's function. So g x eta must satisfy g double prime plus g is equal to delta x minus eta, right? So this is our equation because right hand side is replaced by this one. So with of course the same boundary conditions that g0 equal to 0 and g at pi by 2 equal to 0, and then we have a continuity that g should be continuous and partial g by partial x has jump of 1, right? So this is jump of 1 at x is equal to eta. So this is basically your Green's function problem. So this whole thing should be satisfied. Now when x is, so how to solve it? We basically, this g is not defined at x is equal to eta because the second derivative does not exist. So we have to keep ourselves apart from eta. We have to consider what is happening near eta but not exactly equal to eta. So we have the same differential equation as before, g double prime plus g is equal to 0. So if I write the auxiliary equation has m square plus 1 is equal to 0. This implies that m is equal to plus and minus iota. So your g is equal to c1 cosine x plus c2 sine x. So this type, your function should have this form. All right, but as g is defined differently in x less than eta and x greater than eta, so your g x eta should have this form. Both are a cosine x plus b sine x in this interval, and similarly c cosine x plus d sine x in the other interval, because in both the intervals whenever x is not equal to eta we have this type of solutions. So either x is less than eta or greater than eta. This is pi by 2 because our conditions are from 0 to pi by 2, see, 0 to pi by 2. So our L is pi by 2 here. So you don't have, you cannot write from 0 to L now because L is pi by 2. Our boundary condition is at pi by 2. So this is what we have. Now if you satisfy the conditions that g at x is equal to 0, right, g0, eta is eta, so what is g0? When at x is equal to 0, you will have g0. So what is this? A cosine 0 is 1, so it's just a. So this has to be 0. And at pi by 2, and when x is pi by 2, you have g pi by 2 eta. So that is c cosine pi by 2 is 1, so, pi by 2 is 0, plus d sine pi by 2 is 1. So in this case d will be equal to 0. Alright, so a 0 and d 0. So therefore g x eta will take the form b sine x and c cosine x, right? This is for 0 to eta, and this is from eta to pi by 2. So this is what we are having here. Now we need to use the continuity conditions, right? Now continuity condition, because I have two extra conditions for Green's function. One is continuity of g. Now between 0 and eta we have no problem because sine x is always continuous. Between eta and pi by 2 we have no problem because cosine x is always continuous. So we are having problem exactly at eta, right? So at x is equal to eta is the issue basically. Before and after eta we have no problems. So continuity of g at x is equal to eta. So it means if you are taking the limit as x goes to eta minus g should be equal to limit as x goes to eta plus g, right? So if you are approaching eta from the left or from the right, there should be no jump. All right, so they both should be equal to each other. So from the left means in this interval, if x goes to eta from the left, then you get this b sine x. So you have b sine x on the left hand side. So limit as x goes to eta. On the left hand side we have b sine x, and on the right hand side limit x goes to eta plus we have c cosine x. So now as x goes to eta, this will be b sine eta and this will be c cosine eta. X is replaced by eta. So this is the continuity condition. And now because they both are equal to each other, so we can call them Here you see it's b divided by cosine eta is equal to c divided by sine eta. I can do it like this, and these both should be equal to a constant alpha. Let's call it, say, because if they are equal, if these two ratios are equal, have to equal to some number alpha. So from here, b is alpha cosine eta and c is alpha sine eta. All right. So therefore, gx eta takes the form. So now our Green's function took the form b is alpha cosine eta and sine x, and second was c cosine x. So c is alpha sine eta. So c is alpha sine eta cosine x, right? So this is our Green's function takes this form. All right, so this is the new form. Now again, alpha is still unknown here. What is alpha? We have gotten b and c are reduced to alpha now, right? In first conditions, I got rid of a and d, so b, c were still there. With continuity, these two unknown constants are converted to just one unknown constant alpha. But we are left with one condition, which is the jump condition. Partial g by partial x has jump of -1 at x is equal to eta. So finally, we use jump condition on partial g by partial x to determine alpha. All right. So what is the jump condition? Jump condition is partial g by partial x at eta plus and minus partial g by partial x at eta minus, eta plus 0 or eta minus 0. It is the same thing. Eta plus means eta plus something, which is 0. Actually, we are not adding anything. It's just an indication that we have on the right and on the left hand side. This should be equal to -1. You see, when x is equal to eta plus, it means you are here. Eta plus, you are on the right of eta. So this is alpha sine eta, and the derivative of cos is minus sine x. So you get minus alpha sine eta and sine x. Minus, here you got alpha cosine eta, and the derivative of sine is cosine x, because now you will use the left when x is less than eta. So you got x is equal to eta minus. That should be equal to 9. So now if you replace x by eta, you will get minus alpha, and minus alpha when you replace x by eta, so you will get cos square eta is equal to -1. So from here, alpha, if you take minus alpha as common, so sine square plus cos square is 1 equal to -1. So this implies that your alpha is equal to 1. So now we have completely determined our Green's function. So therefore, the Green's function, the required Green's function is gx eta is equal to cosine eta sine x from 0 to eta and cosine x sine eta, cosine x sine eta when eta is less than x less than pi by 2. So now it's completely determined. There is nothing left here, no unknown thing inside your Green's function. All right. So we first of all we used the given boundary conditions to obtain some of the constants, and then we use the continuity and jump conditions on Green's function to obtain other constants, and we completely determined the Green's function. All right. So it's not difficult. It's really easy to construct Green's function for boundary value problems. Sometimes, depending on the type of the differential equation, it becomes a little complicated. But of course, with little exercise, with little practice, you can master this thing. All right, construction of Green's function. So let's see another example. Let's see another example which is stated on that slide. It's y double prime plus nu square y is equal to 0. y at 0 is equal to 0. So y at 0 is equal to 0 and y at L is equal to 0. So y double prime plus omega nu square y is equal to 0, y at 0 and y at L equal to 0. So again, to obtain Green's function, so gx eta satisfies g double prime plus nu square g is equal to minus delta x minus eta. This is the equation it will satisfy. Boundary conditions, g0 equal to 0, gl equal to 0. So these are boundary conditions. Continuity condition at eta, basically continuity of g in 0 less than x less than L. It should be continuous everywhere. So usually it is continuous at everywhere, but we need to check at x is equal to eta especially. All right, and jump condition. So what is jump condition? That partial g by partial x. Right, there will be jump discontinuity of partial g by partial x. So it has to satisfy all these four conditions. All right, so first of all, let's start with the differential equation. So for x not equal to eta, g double prime plus nu square g is equal to 0, and its auxiliary equation is so its auxiliary equation is m square plus nu square is equal to 0. So m is minus nu square, which is plus minus iota nu. Take for convenience this to be equal to 1. Just to keep things simple, take this equal to 1, and from here your g should be equal to c1 cosine nu x plus c2 sine nu x. All right, so our gx eta should have this form, that we have to define it for x less than eta. So just rename the constants a, b, right, for one interval, and c, d for the second interval. A, b sine nu x, this is for one interval, that when x is between 0 and eta, and c, d cosine nu x plus d sine nu x for 1. All right. So for convenience, we took L equal to 1 here. So now boundary conditions. So x is equal to 0. At x is equal to 0, you have on the left hand side this one. So a cosine 0 is 1 plus b sine 0 is 0. So a will give you 0. At x is equal to 1, you have this one. So c cos 0 is 1 and d sine 0 is 0. Not 0. It will become c cosine nu plus d sine nu. This thing should be equal to 0. All right. So from here, cos 0 is 1, sine 0 is 0. So a is equal to 0. But here you are getting c cosine nu at x is equal to 1. So it's just nu plus d sine nu is equal to 0. So you are not getting one of them to be equal to 0. What you can do is you can get one of you can write one in the other form, or you can write it like this, that c cosine nu is equal to minus d sine nu. All right. So if you divide by sine nu, so c over sine nu should be equal to negative d over cosine nu, and call it equal to alpha. All right. So you can now find the value of c and d in terms of alpha. So this implies that c is equal to alpha sine nu and d is equal to minus alpha cosine nu. So therefore gx eta takes the form, a was 0, so it will just become b sine nu x. A was 0, so first thing is fine. Here c becomes alpha sine nu and cosine nu x plus d. D is minus alpha cosine nu, and it was sine nu x. So this is the case for eta less than x less than 1. We can simplify it like this: b sine nu x And here sine alpha cosine beta, cosine alpha sine beta is sine alpha minus beta. So you can write it as alpha times sine nu times 1 minus x, right? Because it is sine nu minus sine nu x, sine alpha minus beta, sine nu minus nu x. I took nu common, so this is what you got for eta. A little different from previous example. If I just take this as 1 over nu, let's say at x is equal to pi by 2 nu, then it will be exactly same equation. But by taking a different boundary condition, taking boundary condition at 1, this whole thing changed. So now next is our continuity condition. So from 4 coefficients we got 2 unknowns. See, from 4 a, b, c, d, we have converted 4 unknown constants to 2 unknown constants, beta and alpha. And now use continuity condition. Use continuity of g in the interval 0 less than x less than 1. We have to check the continuity at eta only. Why is that? Because if x is between 0 and eta, sine nu x is a continuous function. Between eta and 1, it is again sine, which is a continuous function. So I am not having any problem other than eta. So at x is equal to eta, our function is defined piecewise at x is equal to eta. That's why there may be a chance to get discontinuity at x is equal to eta. So at x is equal to eta, it means I need to take the limit as x goes to eta minus of g should be equal to limit x goes to eta plus of g. All right. So limit x goes to eta minus. In this interval, you have x goes to eta minus. It means you are below eta. So below eta you have sine nu x. So this is b sine nu x equal to limit x goes to eta plus. So eta plus, for eta plus we have this function alpha sine nu 1 minus x. So if you take the limit of this function, this is beta sine nu eta is equal to, if you take the limit, you have alpha sine nu 1 minus eta. So from here you got beta over sine nu 1 minus eta and equal to alpha over sine nu eta. And again, this should be equal to some other function. You can call it beta or a or c. Let's see what I have used, gamma. In my notes it is gamma, so let's call it gamma because you will be seeing the notes as well. So let's call it gamma. So if I say this is gamma, then beta is gamma sine nu 1 minus eta and alpha is gamma sine nu eta. So therefore g will take the form gx eta will become b. It was b sine nu x, but b has become gamma sine nu 1 minus eta and sine nu x, and here alpha becomes gamma sine nu eta, and you had sine nu 1 minus x. So this is what you are getting. And now you see we have converted 2 unknowns into just 1. You see here you still had 2 unknowns, beta and alpha, 2 unknown constant. Now I only have 1 unknown constant. So to determine gamma at the end, to determine gamma, use jump condition, right? So by using jump condition, I'll get the Green's function completely determined, and jump condition is what? Gx by g at x is equal to eta minus, eta plus to partial g by partial x at eta minus is equal to negative 1. All right, so partial g by partial x for right hand side of the eta, x goes to eta plus, so will come from here, minus gamma sine omega eta and nu cosine nu 1 minus x. Why this minus comes up front? Because the derivative of sine is cosine and derivative of inside is negative nu. So that's why I wrote negative over there. X goes to eta plus. And minus this one, this is nu gamma sine nu 1 minus eta and nu cosine nu x. This is at x goes to eta minus. So that is negative 1. Negative gamma nu is common here. So you can take negative gamma and nu common. Inside you'll be left with nu eta and cosine nu 1 minus eta. Here plus sine nu 1 minus eta and cosine nu eta. This is you are left with. So here you see again sine alpha cos beta plus cos alpha sine beta. So it is sine alpha plus beta, right? So minus gamma nu sine alpha plus beta. Alpha is nu eta and plus this is nu times 1 minus eta. So this is beta is equal to negative 1. This is gamma because nu eta will cancel out. So this is just nu. Sine nu is left inside. This is nothing but just nu. All right. So nu gamma sine nu is equal to negative 1. So from here your gamma is 1 over nu sine nu. This is your gamma. All right. So this is your gamma, and now your Green's function is completely determined. So the required Green's function is gx eta is equal to, this was your Green's function gamma. So gamma is 1 over nu sine nu. So this is 1 over nu sine nu 1 minus eta sine nu x, and this is the case for less than eta. And again gamma is 1 over nu sine nu, and it was sine nu eta and sine nu 1 minus x. So this is your Green's function. All right. So this is so you got sine only. There is no cosine at all because cosine has been absorbed in this statement, because this is sine alpha cosine beta thing. So those contributions of cosine is being absorbed in this sine 1 minus x thing, sine 1 minus eta thing. All right. So this is your Green's function for the example number 2. Let's see another example of construction of Green's function. Example 3. See, it's a little different equation. We are taking the same equation, but the boundary conditions are different. You see, here alpha 1, alpha 2 both are not 0. Alpha 1 is 1, alpha 2 is negative 1. Beta 1 is 1 and beta 2 is negative 1. So here y0 and y1, they are not specified, but y0 and y1 are equal, y prime at 0 and y prime 1 are equal. So let's see how these boundary conditions affect our Green's function. So here you see in all previous both the example, let me show you the slides. This example, your Green's function is symmetric. If you interchange x and eta, right? If you interchange x and eta, you will get this thing back. Here, if you change x and eta, it is still symmetric, right? So your Green's function are symmetric in both the cases here. It means it is symmetric kernel, right? But this is not always the case. This may not always the case. All right? So you have to remember this. It may be asymmetric somewhere. All right? So let's see this example and see whether we are getting a symmetric kernel or not. So again, for Green's function, our problem is g double prime plus nu square g delta x minus eta. All right. Boundary conditions are g at 0 is equal to g at 1. G prime at 0 is equal to g prime at 1. These are your boundary conditions. And then you have a continuity condition, and continuity specifically at g, continuous in 0 and 1, right? Especially at, again, we need continuity in the whole interval, but especially at eta we usually have problems. So at there, and then jump condition. Then jump. Jump means partial g by partial x eta plus, and g by x eta minus is equal to negative 1. So jump condition as well. So we need to solve this whole problem as before. We will follow exactly the same steps essentially, and let's see how this Green's function is different from the previous two. So for x not equal to eta, our g double prime plus eta square g is equal to 0. Auxiliary equation is m square plus nu square is equal to 0. So again m is plus minus iota nu. So g should have c1 cosine nu x plus c2 sine nu x form. This type of Green's function we should have. So we can define g x eta in piecewise functions as by giving different names to the constants. A cosine nu x plus b sine nu x for less than eta, and c cosine nu x plus d sine nu x for eta less than x less than 1. Alright, so again, first of all we will use boundary conditions. At x is equal to 0, we have g at 0 is equal to g at 1. So what is g at 0? A. g0 is a cosine 0 is 1 plus b sine 0 is 0, and equal to g of 1. 1 is here. When x is 1, it is this. So it is c cosine nu plus d sine nu. This is what you are having. So now at x is equal to 1, you should have the derivative equal at 0 and 1. So this implies, what is the derivative? A sine nu x, a nu sine nu x, and at 0 is 0, right? And b cosine nu x will be 1. So it will be b nu, and cosine nu x is 1. So right hand side, c nu sine nu x. So this will be minus c nu. At 1 it's just sine nu, and d nu cos nu x, and x is 1. So this should be the case. And again nu can be cancelled here. Nu is common, so you can cancel. So b is equal to minus nu sine nu plus d cosine nu. So we just call it 2. So now we have these two equations in 4 unknowns. See, a, b, c, d. There are 4 unknowns. So minus c. So you have a, c, d and b, c, d. So there are 4 unknowns and 2 equations. We need to solve them. Alright. So solving 1 and 2 simultaneously. Solving these two simultaneously, we will get, first equation is c cos nu plus d sine nu is equal to a. This is our first equation. And minus c sine nu plus d cos nu, minus c sine nu plus d cosine nu is equal to b. These are the two equations. So let's treat a, b to be fixed and c, d to be unknowns. So I can use Cramers rule here. If I use Cramers rule, then c is nothing but the integral of, first I will replace these coefficients by ab, and sine nu cosine nu will be there, divided by the determinant of the coefficient matrix, which is cos nu minus sine nu and cos nu. This should be your c. So c is a cos nu minus b sine nu divided by cos square plus sine square, which is 1. This is the case, and this is 1. And d is equal to, d is only replace ab in the second one. So first coefficients, this cos nu sine nu will remain there, and second column will be replaced by ab and divided by the same determinant, which is coefficient matrix, right? This is simple Cramers rule. 2 by 2 Cramers rule is really nothing. So you have b cosine nu plus a sine nu divided by again cosine square plus sine square is 1. Right, so I got C and D in terms of A, B, and that's what we wanted, because from 4 unknowns we have to go to the 2 unknowns. So C and D are expressed in A and B. All right, so this implies that your C is A cos nu minus B sine nu, and D is A sine nu plus B cos nu. So this is what you get. You see, A cos nu, A sine nu plus B cos nu. This is your C and D. So therefore, your Green's function becomes, Green's function was A cos nu x, A plus B. So A and B will remain there. So A cos nu x plus B sine nu x. This is your Green's function. A and B are arbitrary, still arbitrary. We didn't get any value of A and B. So A and B will remain there. This C and D will be replaced now. So C is replaced by A cos nu minus B sine nu. This is C with cosine nu x, and plus D, and D is A sine nu plus B cosine nu with sine nu x. So this is your second one. Eta less than x is less than 1. All right, so this is what you got. So from 4 unknown constants, I have 2 unknown constants, A and B. So first of all, let's simplify this second expression, and then we will use the continuity condition. So continuity condition will convert these 2 unknowns to just 1 unknown, and then the jump condition will determine the value of that 1 unknown, and we will completely determine the Green's function. So if I combine this A term, I have cos nu sine nu x, cos nu x, and sine nu x. So cos alpha cos beta plus sine alpha sine beta is cosine alpha plus beta, right? Cosine alpha minus beta. So I got is A cos nu x plus B sine nu x. This is your first one. Secondly, here cos alpha cos beta sine alpha sine beta is cos alpha minus beta. So A times cosine alpha minus beta. So this is what you got. And then you have minus sine alpha cos beta plus cos alpha minus cos alpha sine beta. So that is sine alpha minus beta. So minus B sine alpha minus beta. So this is what you got. And eta less than x less than 1. So see, very similar things, only x is replaced by 1 minus x, x is replaced by 1 minus x. So now use continuity to determine A and B, use continuity and jump conditions one by one. Right? So first we use boundary conditions. So we converted 4 to 2, and now I need 2 more conditions. So continuity at x is equal to eta. Why again at x is equal to eta? Because if you look at this function, from 0 to eta, we have just cosine and sine functions. They are always continuous. Again, between eta and 1, we have sine and cosine functions, again continuous. So there is no issue of continuity other than x is equal to eta. So we only have, we may have an issue when x is equal to eta, because at eta we are jumping from this function to this function. All right. So that's why only x is equal to eta is enough to consider. So limit x goes to eta minus g should be equal to limit x goes to eta plus g. So eta minus g here, this is the function. So A cos nu eta plus B sin nu eta. So on the left hand side you got A cos nu eta plus B sin nu eta. And on the right hand side you got A cos nu 1 minus eta plus B sin nu 1 minus eta. So this is what you got. So from these two coefficients I have to find 1. So first combine this a. So in a you got a cosine nu eta minus cosine nu 1 minus eta. Alright, is equal to b. So b has sine nu 1 minus eta, and this will go over there, will become minus sine nu eta. So now you can divide these two things and combine. So if you divide them, you will get a divided by sine nu eta minus sine nu 1 minus eta is equal to minus b over divide this one, so cosine nu eta minus cosine nu 1 minus eta. So again I can call it alpha, say. Alright, so I will be getting a and b in terms of alpha. So a becomes alpha times sine nu eta minus sine nu 1 minus eta, and b is equal to minus alpha cos nu eta minus cosine nu 1 minus eta. Alright, so this is what you got for a and b. So now if we substitute the values of a and b in your Green's function, you will get cosine x eta is equal to, what was your Green's function? This was your, so a and b. So with a it's cos nu x, with b sine nu x. So a is alpha sine nu eta minus sine nu 1 minus eta times cosine nu x plus b, and b is minus alpha cosine nu eta minus cosine nu 1 minus eta with sine nu x. So this is 1, and the second one is, again the second is a cos nu 1 minus x sine 1 minus x, with a minus sign. So you are getting exactly same thing. This cos and sine will be replaced by 1 minus x. Alpha a is sine nu eta. This minus will make a is cos minus cos, and this will be minus and minus. So this will become minus b, and this is plus. Alright, so this will become plus, and this is fine. So in a we are getting plus here, and b is minus. Alright, so this was a little mistake, not a big one. So this is plus. So again a is sine nu eta plus sine nu 1 minus eta times cosine nu 1 minus x, and minus b will make it plus cosine nu eta minus cosine nu 1 minus eta and sine nu 1 minus x. Alright, so this is the case for x between eta and 1. Because this is minus, you see already here you have a minus b, so minus b will make it plus alpha. So now if you simplify sine nu eta cosine nu x, cosine nu eta sine nu x, so one will become sine and the other will become alpha plus beta and alpha minus beta. So the first one you see sine alpha cos beta minus cos, so this one sine alpha cos beta minus cos alpha sine beta, this will become sine alpha minus beta. So sine nu eta minus nu x, so you can call it sine nu eta minus x. The other one is sine alpha cos beta plus cos alpha sine beta, so this is sine alpha plus beta, right? So plus sine alpha plus beta, so alpha is common, so sine alpha plus beta will make it, alpha is nu 1 minus eta plus nu x. So if you take nu as common, it will become 1 minus eta plus x. 1 minus eta plus x. So sine nu eta minus x plus 1. So this is what you got. Alright? So this is what you got for 0 is less than x is less than eta. And second is again sine alpha cos beta, cos alpha sine beta. Again you have sine alpha plus beta, but this time this is sine nu eta minus x plus 1 here, all right, and sine x minus eta on the other side. And here now the next one is sine alpha cos beta minus cos alpha sine beta. So that is sine alpha minus beta. So sine alpha minus beta will be 1 minus eta minus 1 plus x. So it will become x minus eta. 1 and 1 will be cancelled. So you get plus sine nu x minus eta. This is what you are getting, right? So here eta minus x plus 1, I guess this should be eta minus x plus 1, should be x minus eta plus 1. Let's see this one, sine alpha cos beta plus cos alpha sine beta. So this is sine alpha plus beta. Yeah, so eta is minus and x is plus. So in the first one it is eta minus x plus 1, and here again eta minus x, x from here and minus eta. So this is x minus eta plus 1, and here eta minus x plus 1. So after simplification, this is what you got. So now I'm left with only alpha, alpha, alpha. So now I will use the jump condition to find the alpha. So to determine alpha, use jump condition. So jump condition is, that is partial g by partial x at x is equal to eta plus 0 minus partial g by partial x at x is equal to eta minus, should be equal to minus 1. So the derivative of g with respect to x will have both the terms. So alpha cosine nu and with a minus 1. So this will become no, eta plus. So I'm coming from here, first one. Eta plus means x is greater than eta, so I will differentiate this first. So alpha nu and with a minus sign, minus alpha nu cos, or you may keep alpha outside. So it's minus nu cosine nu eta minus x plus 1, and sine nu. So again and here plus nu. So plus nu cosine nu x minus eta. X minus eta. So this is at x is equal to eta plus, and minus, again alpha is common, so keep alpha outside. Sine will become cosine with a minus 1, so minus nu cosine nu, it's eta minus x, eta minus x, and this will become nu cosine plus nu cosine nu, this will be x minus eta plus 1. So at x is equal to eta plus, this should be equal to negative 1. So now if you replace x with eta, so eta and eta are cancelled, so you got alpha times negative nu cosine nu, and eta are again cancelled, so you got plus nu cosine nu. This is what you are getting from here, and minus alpha, here negative nu cosine, again eta and x cancelled. This is cos 0, this is cos 0, sorry, this is 1. So you see eta minus eta is 0, so cosine 0 is 1, so you are left with just mu only. Here again eta 0, so cos 0 is 1, you got left with this one, plus nu cosine nu, because this is gone, so cosine nu with 1 will remain there, is equal to negative 1. And now if you take alpha common, you have minus nu cosine nu plus nu, and here minus minus plus nu, and minus nu cosine nu is equal to negative 1. So it is 2 times nu minus nu cos nu. So your alpha is minus 1 over 2 times nu plus nu cosine nu. Plus or minus? Minus, right? Nu minus cosine nu, nu minus. So 2 times nu minus cosine nu is equal to minus 1. So this is minus. So you are left with minus 1 over 2 nu and 1 minus cosine nu. So this is your alpha. Or you can compensate this minus with this one. So I'll write 1 over 2 nu cosine nu minus 1. Right? It's easy to absorb this in here and don't write minus all the time. So hence your Green's function is, finally your Green's function take this form. Here if I replace alpha is 1 over nu, so it will be in the denominator. So you have to write this whole thing as it is, divided by 2 nu cos nu minus 1. So this is sin nu eta minus x, sin nu eta minus x plus sin nu x minus eta plus 1 divided by alpha is 2 nu cos nu minus 1. So this is your first one, and the second one is sin nu eta minus x plus 1 and plus sin nu x minus eta divided by 2 nu cosine nu minus 1. So this is the case for x greater than eta to 1. So this is your Green's function for our third example. Alright, so same procedure, maybe in some examples little more work to do, but no change in the concept. It's very easy to find out all these things. All you need to remember is your Green's function satisfies the same differential equation, right hand side replaced by the delta function. But again, because we are interested in x not equal to eta, right hand side again becomes 0. You solve that differential equation, use the boundary conditions to reduce the number of unknown constants, then we use the continuity condition to further reduce the number of unknown constants, and finally using the jump condition we completely determine the Green's function. So only boundary condition will not completely give you the Green's function, because there are more unknown constants than the conditions. Usually you got 4 unknown constants, you get only 2 conditions. So this will reduce 4 unknown constants to 2 unknown constants. Now for these 2 unknown constants, I need more conditions. So using the continuity condition at x is equal to eta, we reduce those 2 unknown coefficients, unknown constants, to just 1 unknown constant. And again, I need one more condition, so we use jump discontinuity condition on the derivative of g to find that one unknown constant finally, and we completely determine the Green's function. Right here you can see there is no more unknown thing sitting in your Green's function formula. So this is the Green's function. Again, it is a symmetric Green's function. G x eta is equal to g eta x. So most of the times you get symmetric kernel, but remark is that this may not be always the case. In some physical problems you may see that Green's function does not come out to be symmetric one, but usually in this type of example we see Green's function to be a symmetric function. Alright, so this is how we construct Green's function from the boundary value problems of the differential equations. Next time we will continue with the Green's function, but I will relate the Green's function to the integral equations next time. So what we will be doing is we will be using the Green's function as the kernel in your integral equations and solve the integral equations. Alright, because g x eta and k x eta, they look the same, and usually their formation is also the same, so they can be treated as the kernels of the integral equation, and we will see in next lecture how we can relate these Green's function to the integral equations. So let's summarize what we did today. So basically we defined the Green's function. The main theme of today's lecture was for the second order equation boundary value problem, how to construct a Green's function. So Green's function satisfy the same homogeneous boundary conditions and 2 additional conditions of continuity and the jump discontinuity to go with it. So then we saw 3 examples. This was the first example where this was a little easier one, and we constructed Green's function for this one, and this was a little more complicated than the previous one, and we constructed Green's function for that, and then we went on to construct the Green's function for this more complicated boundary value problem, and we were able to construct the Green's function for that. So look at all these 3 examples again. Try to do them on your own. Close the video, close the lecture notes, and try to solve these 3 examples on your own. It will help you solve the exercises which will be given later on. So of course, if you do practice right now, they will help you do the exercises and the exams, of course, later on. So try to fully understand these 3 examples. How do we construct the Green's function? By using the properties of Green's function. So you have to really memorize the properties of Green's function as well. So with that, I summarize today's lecture. We studied the properties of Green's function, and with the help of those properties, we constructed Green's function for 3 of the examples. And you can pick up other examples and try to construct the Green's function. All right, so with this, I will thank you for being with me for this whole lecture. And till next lecture, that is it for now. So I'll take your leave for today, and I'll see you in the next lecture with more on Green's function, basically. So with that, Allah Hafiz and Assalamu Alaikum.